Yeah. All right. Well, it's always good to be in the field so you can be able to steal people's data right away before they get a chance to do anything with it. So, um, anyway, what I'm going to talk about today is the impact of gravity waves on Anvil Cirrus on the microphysical properties. And as Martina said, this is going to be both analysis of data and some modeling that I'm going to show. And I want to acknowledge my co-authors, Baron Karcher, Sarah Woods, and Martina Kramer, who helped out a lot with this. And a couple other preliminary things. I apologize. I know probably a lot of you have seen this before. So if you're bored with it, you can do other things while I'm yakking. And please interrupt if you have any questions. So I'm going to look here both at the impacts of sort of coherent monochromatic waves, as well as these sort of ubiquitous stochastic temperature fluctuations, mesoscale temperature fluctuations, on the evolution of ice crystal concentration, size distribution, and mass in these evolving Anvil Cirrus clouds. Okay. So a quick outline of what I'm going to cover. First, I'm going to briefly talk about past studies of wave impacts on Cirrus and how this study fits in. And then I want to show some recent high altitude aircraft data showing the microphysical properties of Anvil Cirrus in the tropics. And then the modeling, looking at the evolution of Anvils with no waves, with these monochromatic waves, and with the mesoscale temperature fluctuations. Okay, so in terms of past studies of wave effects on cirrus clouds, I think they can sort of be lumped into two categories. The first is that these low frequency waves tend to determine when and where cirrus forms. And by low frequency, I mean like planetary waves, Kelvin waves, that sort of thing. And there have been a number of studies showing this. I've listed some of the papers here, and these pie charts are from a recent paper by Atlas and Bretherton, basically just showing that when you have these low frequency gravity waves, you're more likely to have cirrus clouds in the tropical tropopause layer. And again, other studies have shown a correspondence where when you have the cold phase of these long period waves, that determines when and where cirrus clouds form in the tropical tropopause layer in particular. And then there's been a whole other category of studies looking at the effects on microphysics, specifically through the nucleation. And the idea here is that if the cloud is dominated by homogeneous freezing, then the number of ice crystals produced is strongly sensitive to cooling rate. And it turns out the high frequency waves really dominate the cooling rate in the upper troposphere. So if you don't include these high frequency waves in your modeling studies, you end up getting ice concentrations that are far lower than what's observed. And again, there have been a whole series of papers that have focused on this effect. So here, well, no, one other paper to mention is by Aurelian Poglajan, where he looked at these monochromatic waves and showed that you can get localization of ice crystals in certain phases of the wave. So here I'm going to look at something different. I'm focusing on the evolution of Anvil Cirrus after nucleation has ceased. And this makes more sense anyway for Anvil Cirrus because the ice crystals are generally generated in the updrafts of the deep convection, and there's really nothing to do with the waves. So I'm really going to be looking at the impact of the waves downstream as the Anvils evolve. Okay, so the next thing I'm going to show here is some high altitude aircraft data from a few recent aircraft campaigns, and specifically HREX, Poseidon, and Stratoclim. HREX was in the Western Pacific, or actually different phases of the campaign covered most of the Pacific, using the Global Hawk and the spec instruments for cloud properties, the 2DS and the FCDP. And then the Poseidon campaign was another NASA campaign using the WP-57 aircraft, similar instrumentation, spec instrumentation, flown out of Guam in October. And then Stratoclam, which a lot of you know about with the Geophysica, flown in the Asian monsoon, and with the Nixie CAPS instrument from Martinez Group. Okay, so starting off with Atrex, this was when we were out at Guam in late winter, early spring, 2014. And there was this typhoon nearby that had kept us on the ground for a few days. So we were anxious to get off the ground as soon as this typhoon kind of passed north of us. But it turned out as we took off here, we went right through, by mistake, right through a band of active developing convection in this rain band emanating from the typhoon. So we climbed up right through this band of convection, as you'll see. So this is a time series over about a half an hour here. The blue is the altitude, showing the climb out from about 10 to 16 kilometers. Green is the temperature, so 230 down to about 195. And then the black dots are the ice concentration from FCDP. And so you can see that through much of the depth of this convective system, you had very high ice concentrations, much of the time greater than 1 per centimeter cubed, and some spikes greater than 10 per centimeter cubed. So lots of small ice crystals in what I would call active convection. The vertical wind speed is shown in red, and you can see there's lots of turbulence and fluctuations on the order of a few meters per second, which suggests that we're in or near the convection, perhaps not in the strongest convective updrafts, but certainly in convective region. And I've picked various segments along here, shown in this color bar below, to show the size distributions. And going to that next. On the lower right here are the size distributions in these different segments, going up through the cloud, with the blues being the lower part of the cloud, and the reds and dark and black being the upper part of the cloud. And you see this clear size sorting where you have larger crystals in the lower part of the cloud, and then you lose those as you go up. Through much of the depth of the cloud, again, you have lots of small ice crystals on the order of 1 to 20 microns. But when you get to the very top, you're starting to lose those small ice crystals, perhaps because of entrainment of dry air, or who knows. This isn't really meant to be a Lagrangian vertical column in the cloud. It's really, we're obviously sampling different parts of the convective systems, but you do see a clear systematic variation with height. Moving on to the Poseidon example, and again out of Guam, there was another typhoon nearby. This was perfect because it was right on our doorstep, but not overhead. So it didn't keep us on the ground, but we could take off and basically get to the typhoon in 20 minutes. So it was ideal. And you can see with the flight track here that we flew back and forth in these bands of convection out at the edge of the typhoon. And I'm going to show a time series again in this section here where the blue and red bars along the flight track are. So going to the time series, same sort of thing. And the altitude going from 14 to 16.8 in this case. The black dots are the ice concentrations again. Same sort of thing, high ice concentrations, particularly in this convective region. And these are the two segments I picked, one in the convective region and one outside it, presumably in somewhat more aged Anvil. And you see the contrast in the vertical winds and the ice concentrations in these two segments. If I then go look at the ice concentrations of the ice size distributions in these segments, you see the same sort of thing in the convective segment. You see a broad size distribution with both lots of small crystals and some larger crystals. And in the second segment here, where you're outside the convection, much fewer small crystals, and your large ice crystals are gone. And even here, it shows some small crystals. In my opinion, you can never completely get rid of the shattering artifacts, so some of these could still be artifacts of shattering off the instrument probe tips. But anyway, it's sort of a similar picture to what we saw in Atrex. And then lastly, for Stratoclim, this was sort of out of Nepal, the very bold Russian pilots flew through this active convection. The black is the flight track here, overlaid on the IR image, and there's very strong convection along the slope of the Tibetan Plateau here in northern India. And they flew right through this. So I'll show, this is the time series. And the blue is altitude here. So there are constant altitude legs at about just under 17 and 17.5 kilometers. And you see, in this case, we don't have vertical wind speed, but I've shown ice water content in red. And you can see in a couple patches here, there are enormous ice water contents, exceeding 1,000 parts per million, even Martina tells me even higher than that in some cases. And so this was clearly lots of ice that had been brought up before from much lower by this strong active convection. And people like Sergei have documented that this was, they clearly went through some convective cores. You can see it in the forward video, as well as in the tracers. You can see indications of strong updrafts and downdrafts. So very strong active convection. Again, in the black dots, you see very high ice concentrations measured by Nixie caps here. And I've picked 3 segments here, 2 inside the strong convective regions, and then 1 in between where you're presumably in Anvil cirrus that was generated by the convection. Again, looking at these size distributions in these segments, see the same sort of contrast where you have broad size distributions in the convection with some large ice crystals and lots of small ice crystals, and then far fewer either large or small ice crystals when you get outside the convection. There's some issue, I'm not sure in this smallest bin of Nixie caps. I'm suspicious that it's polluted by aerosols, but Martina disagrees with me. But anyway, I think that we get a sort of consistent picture here from these measurements, which I think will be interesting to see if the modeling studies consistent with that. One other thing on the measurements, in a number of campaigns that we've had the CPI instruments on board, which give you nice images of the ice crystals. So you can look at the habits. And there's been a general pattern that's been noted in a few papers, which is when you're in the active convection or very fresh outflow, you tend to get lots of small pristine ice crystals as well as larger aggregates. So the larger crystals are really dominated by aggregates in the fresh convection, whereas almost uniformly when you get out in the aged Anvil, you're dominated by bullet rosettes, which is an indication that you've had some in situ growth. The laboratory studies show you need supersaturation and growth to get these bullet rosette growth under the ambient conditions to get these bullet rosettes, as opposed to ice being brought up from below. So that's another interesting contrast that needs some explanation. Okay, so the modeling approach I'm going to use is very simple. I'm using a bin microphysics model. It's kind of overkill 85 size bins, spanning the relevant size range for ice crystals, using one-dimensional simulations with 20-meter vertical resolution. And I'm simulating 2 types of anvils. One is very high cold anvils up against the tropical tropopause, 15.5 to 17.5 kilometers. And another is more typical anvils detrained around 11.5 to 13.5 kilometers, much warmer. And again, this is where the vast majority of convection detrains in the tropics. I'm using a boreal winter tropical temperature profile. And I initialize the relative humidity saturated in the cloud and dry below. And I maintain a low relativity below, so I just don't get a really deep vertical development of the anvil. this really shouldn't affect the results at the altitude I'm looking at. And I initialized the model with broad size distributions of ice crystals guided by the measurements I just showed. Again, very simple physical processes: deposition, growth, and sublimation, sedimentation. As everyone knows here, there's a lot of other processes that I'm not including here that can affect Anvil Cirrus evolution, in particular radiatively driven dynamics, and I'll get back to that towards the end of the talk. This just shows the initial conditions with the broad ice crystal size distribution, again, based on the measurements, lots of small crystals as well as some larger ice crystals. And I assume a constant ice water content within this high Anvil layer, 15.5 to 17.5 kilometers. And again, the lower cloud is a few kilometers below that. Okay, so first I'm going to show some results without any waves, just to show what happens in the simulation and what the physical processes do. So first of all, this is actually a case with growth and sublimation, but no sedimentation. So just focusing on one physical process here. You might think, since I started with a relative humidity of 100% inside the cloud, and I'm not including any sedimentation or temperature change or anything, you'd think the ice crystal size distribution would just be static. But that turns out not to be the case because of the Kelvin effect, which is the fact that the vapor pressure over a curved substrate is higher than over a planar ice surface. So that means the effective saturation ratio for smaller ice crystals is lower than for large ice crystals, because the vapor pressure is higher for the highly curved small ice crystals. So what that means is you tend to, even if your ambient saturation ratio over planar ice is unity, you tend to sublimate the small ice crystals, and the vapor gets transferred to larger ice crystals. You start to lose your ice crystals over time. So the black is the initial conditions, and the colored curves are different times in the simulation. And so you can see you're losing your small ice crystals here because of the Kelvin effect. And as a result, the ice concentration is reduced. So I started with 2 per centimeter cube throughout here. And you can see over this 16 hours that I'm showing here, you've reduced your ice concentration about a factor of 2 just from the Kelvin effect. Now, just to show what this Kelvin effect does more clearly here, this is showing the effective ice supersaturation modified by the Kelvin effect versus ice crystal diameter in this cloud after it's reached an approximate steady state. So you can see that because of the Kelvin effect, you have some significant subsaturation for these sub 10 nanometer ice crystals. And for larger ice crystals, you have a slight supersaturation. So you can see this drives this mass transfer. Now, if I include both sedimentation and growth and sublimation, you can see that the sedimentation really clobbers the larger ice crystals. And a bunch of studies have shown this, that these large ice crystals larger than 100 to 200 microns will fall out of these anvils very quickly, within minutes even. So you basically are losing the small ice crystals by the Kelvin effect, and then you're losing your large ice crystals from sedimentation. And on the right, I'm showing the ice concentration in the solid curves, and you can see that when you include sedimentation, you even accelerate the reduction of ice concentration. And the ice water content shown in the dash curves goes down very rapidly because these large ice crystals carry a lot of the mass. So this is all without any waves. And so I'm sorry, this is all what I'm showing here is for the high Anvil with a mean temperature of about 197 Kelvin. Interesting thing is if you do this again for the lower Anvil with a mean temperature of about 225, then everything is accelerated and this narrowing of the size distribution is more rapid. And you lose your ice crystals concentration goes down more rapidly and your ice water content goes down as well. And this is because these growth and sublimation processes are far faster at the higher temperature. I calculated the rates are about a factor of 25 times faster in this warm Anvil than in the cold Anvil. So everything happens faster, which I think is interesting and affects the Anvil lifetime, as I'll show as I go along here. Okay, so that was all without waves. Now I want to look at the effects of waves, which is the main point here. And again, I'm looking at two types of situations. One with coherent monochromatic waves, which you do see occasionally in aircraft data and in the superpressure balloon data. And modeling studies have shown that you can get these can be generated by convection. This is a figure from one of Joan Alexander's papers. And then the other type of waves I want to consider are sort of these ubiquitous mesoscale temperature fluctuations that are there most of the time as you fly around in the tropical tropopause layer, and I think even other places in the upper troposphere. And these have been documented very nicely by these semi-Lagrangian balloon measurements, the Stradiol campaign. And so we know about the statistical characteristics of these waves. And they really are there much of the time. Okay, so first focusing on the monochromatic waves, what I've done here is picked a simple case of a temperature amplitude of 1/4 Kelvin and a period of 60 minutes. So this is a relatively high frequency wave. Now, what I'm showing here is for the high Anvil, I'm showing the size distributions sort of turned on their side here. So the x-axis here is time going from 0 to 24 hours, and the y-axis is diameter going from 0.5 micron to about 500 microns. And so initially I've got this broad size distribution. The color shading is ice concentration, or dN log D, and you can see the initial broad size distribution. And as I showed in the previous figures, as you go along, you lose the small crystals because of the Kelvin effect, and the large crystals fall out. So you get this narrowing of the size distribution. On the bottom, I'm showing what happens if you include this high frequency monochromatic wave. And you can see you significantly accelerate the loss of small ice crystals. And that's because the ice crystals tend to completely sublimate in the warm phases of the wave. And so you really accelerate the narrowing of the size distribution. And I'll show the overall effect on ice concentrations in a minute. If I contrast that to the warm Anvil, again, at the higher temperatures, the rates are faster. So even without waves, on the top right here, you see the narrowing of the size distribution is faster than in the cold Anvil. And particularly when you get the waves, you basically are narrowing the size distribution to the point where you've got a vanishingly small size range where the ice crystals can survive, and you essentially clobber the cloud completely after about 15 hours. So this can really, I think, dramatically shorten the lifetime of the Anvils if you have these waves. Looking at here for the cold Anvil, the evolution of the ice crystal concentration, the total ice crystal number. The black is without the waves. Again, you decrease by about a factor of 2 over the 24 hours because of the Kelvin effect predominantly. And then the curves are with waves with different amplitudes. Just to show the sensitivity amplitude, not surprisingly, if you have higher amplitudes, you get a greater reduction of the ice concentration. But even with fairly low amplitudes, you substantially decrease the ice concentration compared to what you got with no waves. This is all for the high cold Anvil. And then, okay, showing what happens, this gray curve is what happens if you don't include the Kelvin effect. So just set this Kelvin term to unity. Then you really don't reduce your ice concentrations much. So this Kelvin, it really is dominated by this Kelvin effect that clobbers these small ice crystals. And I think that's an important result here. Then looking at the lower warm Anvil, again, everything happens faster. Your reduction of ice concentration is very rapid. particularly when you include the waves, you lose a lot of your ice just in the first cycle of the wave, and you really reduce the ice concentrations rapidly. Even without the Kelvin effect, you get substantial reduction in ice concentration with this 0.25 Kelvin amplitude wave, because again, you're just able to completely sublimate these small crystals in the warm phase of the wave. Okay, now this was all done with an Eulerian model, so you can't really track the evolution of individual ice crystals. And as I'll show, there's some interesting thing going on with individual ice crystals. So what I've done here to look at that is I've introduced a bunch of test particles with different sizes, ranging from a micron to 70 microns. And I start them all at the beginning of the simulations at 17 kilometers. And what I'm showing here in the gray shading is ice water content in this simulation with the high Anvil versus time and height. And then the colored curves show the time height traces of these individual test particles. So the color indicates the size. So the large ones up around 70 microns bomb out very quickly, and then they sublimate when they get to the subsaturated air at the bottom of the cloud, and the smaller crystals fall very slowly. So now if we look at the evolution of the ice crystal sizes for these test particles, so I'm showing ice crystal diameter versus time here, and you can see the color shading is the altitude, which you don't really need to pay attention to. But what happens with the largest ice crystals is they fall rapidly till they reach the subsaturated air and then sublimate very quickly. The smallest ice crystals sublimate right away because of the Kelvin effect. So crystals smaller than a few microns. However, for this mid-range size of a few microns, up to about 10 microns, you get growth of the ice crystals. And that's again because of this mass transfer from the small ice crystals to the larger ice crystals. And so you actually get growth from a few microns up to maybe 20 microns. And I think this is at least qualitatively consistent with this appearance of bullet rosettes in these evolving anvils. Okay. So lastly, I want to go on to what happens when you use these mesoscale temperature fluctuations. And there have been a couple of schemes developed by Podglegen and Kercher to develop the synthetic time series of these temperature fluctuations that share the statistical characteristics. Basically, they fit a Laplace distribution indicated by the stradial superpressure balloon measurements. So I've used these schemes to generate these time series and superimpose them on the temperature in the model. And since each of these time series is unique, I need to run ensembles to see the overall effects. And I'm kind of using overkill again here. I've run 400 ensembles of 400 simulations here, so I can look at the mean results. Okay, so what I'm showing here, again, starting with the high cold anvil, is the ice concentration again versus time. And I'm using a log scale here for ice concentration. So things look a little different. You can see without any waves, without the MTF, mesoscale temperature fluctuations, you reduce the ice concentrations a factor of 2 over 24 hours. But then when you include these mesoscale temperature fluctuations, it's much more rapid reduction of ice concentration. The different curves are different ensemble members, and the blue curve in the middle is the ensemble mean. So you decrease your ice concentration more than an order of magnitude here with these mesoscale temperature fluctuations. Looking at the bottom at the ice water content, you can see that through most of the 24-hour simulations, the ice water content is not affected much by the mesoscale temperature fluctuations. That's again because it's dominated by the larger ice crystals, which are predominantly affected by sedimentation. But as you get towards later in the simulations, when you've actually lost most of your ice crystals, you start to lose lose your ice mass as well when you include the mesoscale temperature fluctuations. Again, looking at the warmer anvils, the warmer lower anvil, everything's more rapid. You basically destroy your cloud typically within 10 hours when you include these mesoscale temperature fluctuations. So it really limits the lifetime of the anvils, both in terms of ice concentration and in terms of ice water content, because you basically just lost all your ice. So really, I think is an interesting result that you can really limit the lifetime of these anvils if they're lower and warmer. Okay, so to sort of summarize here, this is showing frequency distributions of ice concentration. First, for the high cold anvil, the initial conditions are shown in black here. So I started again with just a delta function at 2 per centimeter cubed in the anvil. And if I don't include the mesoscale temperature fluctuations, you get this green result here, where you reduce your ice concentrations by a factor of 2. If I include the mesoscale temperature fluctuations and the Kelvin effect, shown in blue here, you get more than an order of magnitude decrease in the ice concentrations. And if I include the MTF but don't include the Kelvin effect, you really don't reduce the ice concentrations nearly as much. So again, showing the strong importance of the Kelvin effect in what's going on here. And so these colored curves here were at a time of 8 to 12 hours in this cold anvil simulation. Do the same thing for the warm anvil, but here I'm showing the results at 4 to 6 hours because everything happens much faster. And you can see same sort of thing. Not so great reduction without waves, but still significant. And then with the waves and the Kelvin effect, about a factor of 20 reduction in ice concentrations. In this case, if I include the waves, but don't include the Kelvin effect, you get a very broad distribution of ice concentration, some simulations with little or no reduction in ice concentrations and some with dramatic reductions in ice concentrations. So again, the Kelvin effect is very important here. Okay, the number of caveats, which I want to get back to here. There are other processes such as entrainment of dry air that will reduce ice concentrations in anvil cirrus. I tend to think this would happen primarily right near the active convection where you've got very strong turbulence. My suspicion is once you go down into the anvil, the turbulence dies down very quickly and you don't get a whole lot of entrainment. But again, this is something that needs to be addressed with cloud resolving models. And speaking of which, there are other processes such as radiatively driven mesoscale circulations and turbulence, even out in the aging anvils that can drive temperature variability, which will presumably do the same sort of thing as the waves in terms of reducing ice concentrations. So that again requires cloud resolving modeling. And I think with these, for anvils that persist for many hours, I think you've really got to have meteorological support, mesoscale and synoptic scale uplift, which I haven't included here. So that's another thing that needs to be examined. And especially for anvils that persist for very long times, I think you've got to have fresh nucleation of ice crystals occurring. You can't just have the population of ice crystals brought up by the deep convection and have that persisting for days. I just don't think that's possible. Okay, so to summarize, I think these gravity wave temperature perturbations can definitely reduce the ice concentrations in evolving anvil cirrus, either with monochromatic waves or the sort of random temperature fluctuations that you get away from strong sources. And this is really caused by an interplay between the waves, growth and sublimation, sedimentation, and the Kelvin effect plays a key effect. And the Kelvin effect actually causes mass transfer from small ice crystals to large ice crystals. So you get growth of these mid-range ice crystals. The wave impact is much more pronounced in the lower, warmer anvils. So I think that's interesting. You may get a dependence of anvil lifetime on its height or temperature. And I think these results are qualitatively consistent with the measurements of size distributions and habits in the aging anvils. And as I mentioned, the appearance of these bullet rosettes requires growth of ice crystals and supersaturation. And of course, as we all know, these high frequency waves are generally not resolved in global models, certainly not in the GCMs or analysis models, but even in these global storm resolving models. Rachel's paper with Chris Bretherton showed that even most of these global storm resolving models are sort of woefully deficient in these high frequency waves. So this is sort of key for these models to either resolve these waves or somehow parameterize them to properly simulate the evolution of cirrus clouds. So lastly, I think there's some follow-up studies that could be done here. This was a 1D simulation, I think including wind shear is important, and people really haven't done a whole lot looking at the impacts of wind shear on anvil cirrus or cirrus formed in situ. As I mentioned, clouding model resolving model simulations could sort of do the whole problem, the deep convection, realistic waves generated by the deep convection, and the evolving anvil cirrus, which includes the waves and the radiative dynamical feedbacks. And then lastly, I'm kind of excited by these approaches for tracking anvil cirrus in the geostationary satellite imagery. And one thing you could do with these tools is investigate the dependence of the anvil lifetime on the height and temperature, which is suggested by this modeling study. And I think there was another one that hypothesized such a dependence as well. So that's all I've got, and I'd be happy to take any questions at this point.